healthy, staying safe. In a bit of a hiatus from our sessions.
for you.
Apologize for that. Didn't find a good date, but glad to be just chatting with all of you again. Always enjoy your questions. Today is going to be a somewhat light presentation compared to the others, but just to kickstart again the session. And then come September, maybe we look for one more date. I try to look into the topics that Yong Kang and Husni has suggested. That might be a new trade on that. So today I'll actually be talking to you about a little bit of sharing on object detection with networks. This is basically a repeat of a training I gave for Signal Processing Society School. So quite anticipating some interesting questions today because I know many months ago, Beijing was looking into this, and Husni is recently a bit interested in this as well. Okay, so just feel free to interrupt me at any time. Okay, this is meant to be open discussion. It's knowledge sharing. All right, to get started, everybody is familiar with the standard classification task. Right? By now, we know that deep neural networks is a great tool for image classification. You can train, you have a certain number of classes, you have your training images. You can say, okay, like in this image, there are cat present, no cat present, there are vehicle, and by extension, Petroff's style of work is a specific kind of defect of the PCB board at present or not. And a further refinement to the classification problem is you classify, saying that there is that object there, and then you try to localize it. By localize it, we mean some way of actually indicating the position. So I just want to get the clear point that we are now going towards more detailed level of localization. And the reason these first two are captured in the first, just the first, the left half, they are distinct is because classification typically you can only find one class in an image. So if, for example, your classifier can detect cat and grass, it will be forced to choose only one category for this image, even though both categories are present. So let that distinction be very clear. So there are ways to work around this. There are multi-class classifiers and stuff like that. But the generic classifier normally is one class per image. Okay? And when we start moving into more refinement, I think the space that we probably call object detection is you're able to get multiple classes in the same image. That means there's a cat there, there's a dog there, there's a duck there. You can say there's a cat here, there's a dog here, there's a duck here. Because the idea behind object detection is I want to localize the object. Therefore, if I can localize the object, I can detect more objects in the image, right? And again, here I want to actually just make this point really clear. It's not so much about drawing squares or things like that, right? You could actually develop neural networks to draw circle and stuff. It's more of the question of localizing the object. And people find that the square is a convenient measure why they start because everything is pixelated. But if you're not confined to square and all that, it's just this idea of localization. So object detection, we're talking about classifying the object and localizing it by giving you a square. And typically, when we get square, I hope you understand that there are many ways to specify a square or rectangle. One is you can give just the four edges, okay, that completely specify the square. Or you can give the center point, and then you can give the width and height. That should also classify the entire square and so on. So there are multiple ways to actually specify a square. So you just have to realize that it's not that you're putting in every pixel of the square. You're just finding a way to localize the object. So even if you find the center point of the object, the weighted mean, something like that, that's also a way of localizing the object. It's whether more fine localization or more coarse localization. So with object detection, we're generally talking about coarse form of localization. And the finest form of localization for images is actually segmentation. Because segmentation, you are directly saying which pixel belongs to this object. So it goes back to pixel identities, and you can even take into account things like occlusion. Like for example, this second dark brown cat here is partially covered by this front cat, right? But if you say object detection is assuming this object is kind of symmetric, so it's just drawing a bounding box around here. In instant segmentation, you're going deep, you're just saying which and every pixel itself, what's the identity of each pixel. Okay, and so the first distinction is when you're moving from classification to object detection. The first distinction is how precise are you in your localization? How precise are you in your localization? And the second distinction is, are you able to actually detect multiple instances of an object? So what do I mean multiple instances? Here, for example, can you tell me that there are two cats versus there are one cat, right? So in the classification problem, because you're not localizing, maybe it doesn't quite make so much sense. Well, is there one cat, two cat, three cat, four cat? You just at the general level, there's a cat there, then I classify it. But when you're talking about again object detection or on the extreme end segmentation, it starts to make sense because you have localization, you can also start thinking about numbers. How many units of this object is present in the image and where are they? So the dimensions of where we can improve object detection are in the precision of localization, and number two, the number of instances. Can you accurately predict the number of instances of that object? And it's a bit more complicated than that. When you actually do multiple instances, because you have to start looking at things like you have to know enough that this is not just the pixels, that look like cat. There's a certain color distribution and all that, but you have to know that there are actually like 4 ears in this kind of bunch of pixels here rather than two, right? So that there are actually two cats, not one, right? So and then there's also occlusion, because sometimes the cat will the ear, like this ear sort of looks like it's merged here. So how do you know that there are 4 ears rather than three, right? And then if it's 3 ears, you know that probably it's just two cats with an occlusion, right? So this problem of actually overlapping objects of the same class is really, really tricky. It's something that you should look out for when you're looking for fine-grained object detection strategies. Of course, if your objects are very far apart, very well spaced, boundaries are defined, you're okay. You start to have problem when the objects are actually overlapping. Some of the objects may be occluded, that means you don't see the whole object. And the worst case is if you have multiple objects of the same instant type that are overlapping. I think that's actually the most difficult case to detect. Okay. So now this is the landscape. This is the landscape of what we want to try to do. And rather than going for instant segmentation, the open question is saying, okay, we maybe need something with the intermediate accuracy, and that was where this object detection is born. Is born from that. Okay, and before that, I also want to just recap with you, so that you have this picture in your eye. How does convolutional neural networks look like? How do we look at the weights and all that? This is just to recap why, because we're going to go through some network architectures and just how they are permuted and how the key ideas behind them. So it'd be good to just recap the understanding here. Why? Because I think some of the ideas from object detection, how they derive the network, could actually give you new ideas how to apply or modify your CNN for even other types of detection tasks. Maybe even it could help you also with simple classification tasks, right? Okay, so the idea is something like this. You have an image here, and you have your weight here, and this weight is called your convolutional kernel. And the reason it's called convolutional neural network is because this weight looks like you're convolving across the image. You're sliding it over the image, and then you're just multiplying like this voxel multiplied by this pixel, this voxel multiplied by this pixel, this value, this voxel multiplied by this value. Then you sum all of that out, you get one value here. Then you slide it again. What it actually looks like from a neural network perspective is, okay, I want you to understand this. This is a very, very important point. This is the output of a neuron. These are all the inputs of the neuron. What you're pretty much saying is that this neuron that is giving this output has all the weights connected to this region. And this neuron, giving this output, has the same number of weights connected to this region, but they are repeated weights. So convolutional neural network is it's actually at its heart, it's a dense neural network here, but it's implemented as convolution, and you need to understand the way this from neural networks is just imposing a repeated weight constraint. Okay? But the nice thing about this convolutional kernel, interpreting it as a convolutional kernel, is that you can extend it. Okay? You can have a convolutional kernel. So this is again this kernel, but now because you have multiple dimension image, and again multiple dimension image is up to you to give the interpretation. Most commonly is color, RGB, but it could also be images from a different camera location, like some of your geometry. It could also be images with under different illumination, different lighting color, different lighting position. It could also be images from different site or from different object board types, but the same class with the same machine. Or it could be images from different machines, but of the same board. It's up to you to define multiple channels. It just means that the multiple channels have distinct information. And here the idea is that if you have a different channel, you will have a different set of repeated weights. Okay, so this first filter is the filter that's applied to the first channel. Okay. The second blue filter is applied to the second channel. The third yellow filter applied to the third yellow channel. Fourth yellow green filter is applied to the fourth channel. So this is an extension of this concept of doing convolution on neural network. But this idea is kind of nice because it's actually saying something like, I'm going to perform a repeated action on a block of the inputs. Okay, so these inputs are all your synapses. And for the neural network, that action is actually multiply, accumulate, non-linear mapping. You could also think about it as a max pooling. That is, I select a maxima within this region, or a minima, or a rank value. So it's more generalizable than just multiply, accumulate. Is this idea that I'm doing a repeated operation on a block throughout the image. So that's the key idea. And this idea is very powerful because it's just a very more efficient way for, it's powerful because of two things. Like, number one is a sort of an efficient way for us to perform the computation because we can reuse a lot of the signal processing type of acceleration, right? And we know that if I'm just convolving across, this is a massively parallel operation. I can actually convolve across the entire image. I can just have, do the convolution in parallel, right? So it's massively parallel, right? And it doesn't just need to be convolution. It could be doing comparison, like the max value. It could be doing a kind of thresholding, or many different things we can do. But the idea here is that because the deep neural networks are so large, there's so many parameters. Because you're defining repeated operation, the same operation on each block, you're reducing the dimensionality, you're reducing the complexity of the problem by imposing the constraint of common weights. So this is a very powerful idea. Like you could just sit on that and solve that. Okay. So having done our recap of convolutional neural network, and the key take-home point is basically it's just a common operation over some kind of block here. And it's kind of nice because if you define this as a repeatable operation, all of a sudden you are no longer bound to the size of your data, right? Because you're saying that it's the same operation that I'm repeating throughout whatever size of the input. So if I actually have double the input size, I can run the same filter with the same either convolution or with the same comparison to get the max pooling. I'm not really now constrained by the size of these. That there's no such thing as a fixed size thing. The fixed size of the input only comes into play when your weights are distinct. But when your weights are repeated across the field of view, this becomes not a problem because it's repeated, so you can scale this arbitrarily. And that is a nice feature that you will see has been reused very, very effectively in object detection networks. We'll talk about that a little bit later today. Right. So now I'm going to jump into a survey on the object detection feature. Basically, I'm going to be discussing two trends of network and the associated variation. One trend is basically, it's just like a one-step kind of object detection. We put it into a deep neural network and boom, out comes the localization. That is the location of the object as well as the class of the object. The second class of solution actually is sort of split roughly into a two-step process. The first step process is actually looking at suggestions of objects. Where could there be an object in the image? Just give me all the possible suggestions. Then the second step would be, for each of these suggestions, you rank. Is there really an object there? What is that object there? What is its precise location? Okay, so object detection, there are two general strategies from neural network. Of course, for machine vision, there are a whole lot more, but I just try to focus on the recent advances that have been so successful in literature. So two general approaches. The first approach is actually from the RCNN part. That is, you're just splitting the problem into two. One, you get some suggestions of where could there be possible objects, and then you go and check each of these possible locations and check whether is it of type this particular class and can I refine the location? And the second is exemplified by YOLO and SSD, where it's just kind of one step all in one. But you can't quite say it's not doing these two steps. It's also still doing these two steps, but it's not this thing. It's not something that you can speed it up. So what I found is that roughly these two steps again, sometimes like YOLO and SSD is doing everything in one go. Like ICNN is actually doing it too, but they're actually kind of four distinct things that are happening in the network. Like one is the region proposal. That is, you look at the whole image and then you just try to identify patches or regions where there might be an object, and then you try to find the best representation of features of that object. And the interesting part about this idea is somehow you are doing this region proposal without any idea of what kind of object you are looking for. So when you're training the region proposal part, or you're developing the algorithm for that, this class agnostic, meaning doesn't actually care what class. It's not actually, it's solving like a chicken and egg problem in my mind. It's like you're not even saying what are the type of objects I'm looking for. You don't know whether it's animals, it's vegetables, it's cars, it's ICs, right? It's just saying that give me suggestions of things that look like an object, right? And I'm not even going to tell you what that object are, and give me a good way to represent its features. So it's sort of you're forcing the network to actually learn to recognize objects without even saying what the objects are, and then get good features for that. So in a way, it's kind of like, to me, it's very surprising. It's like it's totally like exact opposite of what you do in classification. In classification, you actually say this is the type of object I want you to learn. You learn the features for that. Here, you're just sort of like, I'm not going to tell you what these objects are. You just learn and tell me where the objects are and what are the good features that could represent the object. And then what this first category is doing is, after you've got these features, you refine. You start saying, okay, I've got some good representation of the object features, although I don't know what this object is. So if in that case, it means that your feature representation has been really, really powerful, really, really descriptive. So from that, you just say, okay, is the objects that I want to classify, do they really exist at this region? So that's this reason classifier part. And if it exists, let me try to give it a shot to refine the location of the object, right? Because again, the region proposal is basically getting a rough kind of region where the proposed object is, but it doesn't take into account any kind of information about what is the type of the class of the object and all that. So once you actually can identify the class, it stands to reason, if you know the class, you probably can do more and look at more of the features representation. You can actually refine your estimate of the location. So again, you have the features and the location, the decision on the features, and the location refinement. Okay, so I found that object detection will have these four kind of steps, usually. And we go to what started this idea in the first place. It's called the ICNN, or it's the region-based CNN. Not to be confused with RNN. RNN are recurrent neural networks, different architecture. These are region-based CNN. And it's from the Gershik paper in 2014. I give you the link here. And here, the idea is just going to roughly share with you what was the four steps that they will apply for this type of to make this work. So for the region proposals, again, just to remind you, the first two steps, region proposals and feature extraction, this is class agnostic. That means at this point, you're not even training, you're not even telling about anything about what is the class, whether you're trying to detect force or what. It's just saying that, tell me something that looks like could be a region and give me good features for that. And then you have the classifier and bounding box. So this contribution of this paper was it's a powerful paper, but it was a relatively primitive approach because the region proposals, they actually use a heuristic algorithm. They call it the selective search, and they actually just made the bounding box. The region proposals were actually given as bounding boxes, and they just actually specify the bounding box to have a bit of extra pixels around it. And the feature extraction, this is where they started to use the novelty on the CNN. At that point of time, it was AlexNet, trained on ImageNet. So we're talking about 5 layers CNN with two fully connected layers only. So the innovative part about this is, after they detected the bounding box, they used a standard heuristic algorithm to just generate a bunch of proposals. Like I think it's about 2,000 odd or 2,000 odd proposals per image. Like. And then what they do is they will do an affine transform on the image. That is, they just stretch and scale the image so that it ends up hitting a 227 by 227 image size. And then this is the way they make it into a fixed image size that the AlexNet can take. And AlexNet's job is not to classify anything, it's not just to get features. Okay? And once you got the features, okay, so every region that could possibly be an object, you get the features out of that. And that would be the input to a new set of classifiers. They just apply a very simple support vector machine as the region classifier. And what they do is they also learn a regression model to correct the size of the bounding box from the region proposal. So this second step here of the class specific one is you can think about it more as like it's adding a little bit extra to update the results from the first two. The region classifier is adding, probably you can view it as an additional decision layer onto the feature layer of the feature extraction. And this linear SVM is actually trained more towards the clusters. Whereas the bounding box regressor, again, you all also understand that regression is also can be framed as a neural network problem. It's just trying to update the position of the center, width, and height of the initial region proposal itself. Okay, so if you just look at it a little bit like this, you can say like more or less this region-based CNN, RCNN. The key idea is that I have a general approach to actually generate something like 2,000 over boxes like this that could potentially be an object. And I have a way I warp it until I can get features out of a CNN to extract these features. And then I add on an SVM and again, maybe a very simple single layer neural network, which is a bounding box regressor. Of course, they didn't implement this as a neural network, they implement this as regression, but regression can be a neural network, at least to just kind of refine the decision. So it's kind of an interesting strategy that maybe one of the approaches would be to go for general region and object-based feature representation, and then you can refine it with a objects class-specific layer for it. So it could be an interesting way to approach things. And I just wanted for completeness to go through the algorithm for region proposals. It's actually coming from selective search. And this idea here is that the way you define a region, there are many ways to define a region. And so you can actually just kind of look at heuristics of what the regions, what could actually be like the suspected areas of an object. Okay, and here, again, among the heuristics, you can look at similarity or the variation in color and texture. Okay, so there's a similarity in texture, similarity in color. Then you can look at what they call enclosure. If there's the pixels within the sort of a bounding box of a larger region proposal, most likely those two are the same region. And you can also look at that there are properties at different scales. So what was the selective search algorithm, which is this part here, the region proposal part, nothing to do with neural networks at this point, it's just finding a bunch of boxes that may contain an object, even though you don't know what the object is. It's actually just getting a bunch of similarity strategies. So again, they're looking at consistency or similarity of light intensity, shadow, highlights. They actually look at it in terms of different color space. So they're looking at color space invariance. They're looking at similarity or texture invariance using shift-like features. They're looking at things like, is the region or bounding box similar? So they start with a group of region proposals for roughly the same size, and then they start merging them. And then in this way, they can actually reach what they call multi-scale region generation. So this is just included just to share with you the first proposal of RCNN. Everything else was not neural network except the region feature extraction. But the interesting concept was, how are you actually going to propose regions that may potentially contain objects without even defining what those objects are? Okay, so RCNN is, of course, this is a good idea, but it just didn't work in practice because it was really time consuming. And why is it time consuming? Well, let's look at this. The first, the way the regions are proposed is actually heuristically based. Okay. And it takes time because you need to generate, look at the whole image and you do the merging and all that. And then you look at it, I need to actually run my feature extraction for each region, because each region proposal, I need to warp it and then run it through the deep neural network. So if I've got 2,000 regions, I'm running the LXNet 2,000 times. If I've got 8,000 regions, I'm running LXNet 8,000 times. So this is a pretty inefficient way of running LXNet. And then, of course, we look at the region classifier and bounding box. These are algorithmic. But then the question becomes, we think that deep neural networks can do everything. So is it possible for us to actually look at how to convert everything else in terms of deep neural networks? And the answer is yes, it's possible. But for the first part here, I want you to actually focus on the fact that the feature extraction deep neural network is actually run multiple times for each region. You get the features from each region. And that, if you think about it, that's pretty inefficient, right? Because again, the whole idea of deep CNNs is you get the feature representation of the whole image, right? So if you can get the feature representation of the whole image just with one step of inference, why do you want to run the network on different region sizes over and over again for different proposals? And so that's what we try to address here. And the key challenge here is, okay, supposing you start saying that instead of actually trying to run the CNN over and over again for each region proposal, I run it once and I get the features of the entire image, and then I figure out a way to extract the features of interest I want for that particular region proposal. Can I do something like that? And it turns out the answer is possible. Okay. But the question here, the main difficulty is that my regions are of different sizes. I don't have a fixed size region, and the whole reason why we got RCNN got this to work was because it managed to fix the region size by doing an affine warping. But obviously this is not great. So is there a way for me to actually extract features of different size window to give me a fixed size feature representation? So I don't want to do resizing of the region, right? Because it doesn't make sense, right? Because in the first place, I'm trying to reduce the number of operations to get the features already, right? So I just do one CNN on the whole image, and then I should be able to get that. So this is where the next paper, Fast RCNN, is a little bit clever. What it does is it actually says, yeah, I have a technique that allows me to convert boxes, regions of different sizes, to a feature representation that is always of a fixed size. And that is technique they do a pooling, a max pooling. And again, the pooling function, if you think about it, as I told you, it's just this window size. You just select one value out of within this whole window size to be the output of the image. And if it's max pooling, the value is the max. So the intelligence of fast RCNN is that I will have regions with different bounding box size. So in that case, I will define windows, pooling windows of different size, subject to the regions, but I have the same number of pooling windows. So I will have extracted the same number of feature representation, so a fixed size feature representation, no matter how large or how small or how variable the region proposal. So is that part quite clear? The intelligence, how fast RCNN was able to kind of solve that difficulty with RCNN?
Yes.
Okay, so I think this is kind of nice because it's giving you this idea of how, most of the time you start the traditional LXNet is just, I'm just doing affine resizing. But I think what was intelligent about fast RCNN is this idea that the kernel, the window of your CNN, I can define different operations. And basically those operations are nothing else but finding some kind of summary of the patch here. So what they do is, if I need a fixed size feature vector and I have variable size input window, I can change my window size, but I can still perform the same summary operation, whether that summarization operation is weighted multiplication and addition, as in the case of convolution neural networks, or it could be a max pooling. That means I'm just comparing to get the max value. But it's this key idea, this very interesting idea that I can always transform a variable size input into a fixed size representation, feature representation, using this pooling idea, which I think is very interesting, very cool, very interesting. And because I actually have fixed size feature representation, I can now define my region classifier and bounding box by fully connected layer. See, the implication is there. Like previously, the way I get fixed size feature representation is I make my regions to be fixed size, but that's not great lah. You sacrifice certain things. Now I don't make my regions fixed size, but I summarize. I do a pooling operation with different size windows so that my feature representation is fixed size, and then that allows me, because now I got a fixed size input, I can use fully connected neural network layers. And later on, we'll see this will get solved as well. It will actually say fully connected layers is what is restricting you to get fixed size inputs here. But later on, you'll see that it can actually be defined, everything can be defined convolutionally, and we get rid of this idea of fixed size feature representation. So out of this, you get a fixed size feature representation, which is this red color box. And this fixed size feature representation is the feature representation for every single region proposal. So the 2000 region proposals for one image, you have 2000 feature representations. But the nice thing about this is you are not recomputing the features. You're just doing that one step of max pooling to get the fixed size feature representation. And here they add additional fully connected layers. It's just to further transform the max pooling layer to allow further representation to refine the feature representation. So this fixed size feature representation is not taken just as is. It's actually converted into a feature vector through two fully connected layers. That's fair. So the key contribution of fast RCNN is they remove the inference of LXNet 2000 times on 2000 regions on a single image. They remove it by just saying, you do one round of convolution, deep convolution of this, you get the complete feature representation. And then you extract through a max pooling operation with different window size, different feature representation. So you're only running this portion multiple times for each region, but the feature extraction part you only run once on a pre-trained deep convolutional neural network. And now it's nicer because we've converted the region classification, no longer SVM, it's just a simple softmax fully connected layer. And the bounding box is also a fully connected layer. Okay, so this is interesting, it's nice, and it's much faster because it's all fully neural network, so you don't have the uncertainties behind bounding box regression, or you don't have the multiple times of the LXNet to run on the image. Okay, and the other interesting point was you have two types of different decisions that you're making on the output. One is yes or no, which class does this region contains which objects of which class. Okay, that's one decision. The second is refine your estimate of the object of this class. Okay, and the way it's actually trained is the classifier. These two classifiers are trained. The regressor and the classifier are trained simultaneously using a multitask loss. So I think what was interesting about this is you, based on the same feature representation, you can actually define different output tasks, and you can train it simultaneously. Why? Because you think about why you'll be training simultaneously, because you're trying to find the best features here that can jointly help you in task 1 versus task 2. So this is one reason why you probably want to train them simultaneously using a multitask loss. Okay, multitask loss. So that means that the weights of these fully connected layers and these fully connected layers are set depending on the joint loss from the accuracy of the classification and the accuracy of the regression. So this is another generalizable idea, is this idea that, okay, if I got a good lower level feature representation, and if I want to train on multiple different tasks, okay, so and here the simplest I can actually relate this to, maybe like a list of like 9 or 10 different standard IC kind of faults or errors like displacement, right? So you're developing a classifier for that. So why not to consider, having a multi-pass loss, for final SVM layer, for final fully connected layer, drawing off the same feature representation. So I think these things that we can learn from these network architectures to see whether it could help in the other parts of the trucks applications. But of course, I've not had an in-depth discussion with you guys on the applications about 2 years now, so I might not be so updated on what you are. Okay, so here the fixture extraction, classification, and localization. That means these three here are all neural networks. And the nice thing about specifying the operation in terms of I'm doing something on the kernel, and this kernel is movement, everything is back propagation proof. So if you can actually propagate everything by back propagation with gradient descent, it means you can actually use gradient descent to optimize and set the network weight. So that's a very important parameter. Like anytime you want to introduce anything that's a neural network in multiple branches, you just have to make sure that whatever layers or whatever networks that you have defined here is amenable to back propagation by gradient descent. So here I just want to flesh out, this is an example of the multitask loss. That is the loss function that's guiding the setting of the weights here. And again, just to recap, this loss function, you take the gradient of this loss function with respect to every single weight. That's the gradient descent process. And then that tells you how much to switch each weight. And then as you do this iteratively, you'll be able to get a mark for your network value. And basically, what is this loss function? That's the cross entropy loss for the class. So this is standard cross entropy for class accuracy. And here is kind of interesting. This is actually just an L1 loss. That means you take the difference between the location of the true bounding box versus the actual region proposal here. And then you take the absolute value of that. That's the L1. And here is interesting. What this is doing is there's this weight here is saying that you only apply this multi-class loss for classes that are not background. And this is a problem that hopefully at the end of today's session, I need to motivate this. One of the key challenges of object detection is you typically have many more examples of pixels that are not a class. Basically, they're background. Okay, right? Because you have pixels that you have certain classes, like you have a human being, you have horse, you have house, right? But everything else in between, all those things, those are background pixels. They are not a class. So there is a class asymmetry. There is a data asymmetry hidden in all object detection problem that you become very, very good at predicting non-class objects, and then your classifier is basically useless. So here, the multitask loss, they want to try to control for it. They are only applying this bounding box accuracy regression only on the non-background classes. And that's what this term means. It's just a fancy term for saying apply this for those that are not in the background class. Okay. So fast RCNN is okay. Everybody can understand, right?
Yes.
Yes.
Okay, great. So now that we have this, and then we start to ask, we look at this with our critical eye, we say, you know what? This convolutional deep CNN here, right? I'm only using LXNet in 2014, 2015, 2015, because that was the state of the art then. Today I have Inception, today I have ResNet 101, and today I have got very, very deep 100, 200 layer networks. Why do I need to use such a shallow network? And you're right, you wouldn't need, because you got a very, very good, very, very advanced pre-trained networks now. And then here is the question. If you look at this, you're only extracting the features out of the final layer of the CNN, which means that you're only extracting features at the coarsest level, at the highest scale. That means it's not high resolution features, it's low resolution features. And what's worse still is at the final layer of this full image of the CNN, you are doing some kind of max pooling operation to get a fixed size feature representation. Right? So these two effects itself are just telling you that I'm really only making the decision from very, very coarse, large scale features, and it's not even doing a good job at that. But still, fast RCNN does something, and it was the state of the art at that time, right? So the question is, can I do better in terms of uh, pushing the good features out to my classification and my bounding box regression? Because this idea again, I'm doing this classification and bounding box regression. These are class specific training. It's just these few additional layers are improving on the decision to help me to improve the decision based class using a very generic feature extraction. But now my complaint is fast ICNN. I'm just taking the last layer of the deep CNN, and the last layer of the deep CNN, I'm max pooling on that last layer over a region. So it's really, really coarse features. And they are asking the question is, can I do better? And the idea is yes. SPPNet is one example of how they try to propose you to do better. So the idea of SPPNet is called spatial pyramid pooling. It comes from multi-scale filter banks and wavelet theory. This idea that in order to get cost, if you think about it, let me go a little bit further here. All right, never mind. I don't have a good diagram, but let me give you a little bit of background in multi-scale image processing and machine image processing. Okay, is this idea that objects come at multiple scale. So when you take an image at one particular scale, what I mean? I'm meaning that my pixels, the spacing between the pixels have a specific measurement. Okay, so for particular, if I'm taking an image in a particular camera, if I'm at a fixed distance from the object from the camera, my pixels that from the left to right, my pixels are at a particular size. So I'm saying that if this guy is, let's say, like 1 meter away from the camera, this eye here and this eye here, there's a fixed distance that I can calculate. And of course, depending on the optics and all that, if this guy is 20 meters, of course, that distance will change and all that. But each image actually comes inherent. There's a particular scale at which it's measuring things. And if I want to actually find out features, what you're actually designing in terms of filters, like you're saying, I have a filter of how many pixels here. You're actually saying this filter is capturing features at a particular scale. Okay, so if I want a coarser scale, what you actually need to be doing is you need to have a filter that will look at a larger portion of the object. So if I have a very small filter here, it's a small portion. If I have a larger filter that's around here, then it's at the scale of the head. So the head, the scale is about 30 cm thereabouts, 20, 30 cm thereabouts. If I want to actually detect whole person, I need to have an even larger scale. So I need to look at like 1 meter type, 1 to 2 meters type of length scale and all that. This is what we mean by scale. But in image processing, we understand that computationally, yes, I can always resize the filter to make it up, but actually there's no point. Why? Because if your filters are at the large scale, it's no point for you to look at the small scale filters. So what they actually do in the other way is they keep the filters the same size and they downsample the image. So what do I mean by that? So if I want to perform, if I'm actually doing a filtering on the image here, so let's say this image here I have like 25 boxes, 5 by 5. Okay, that's great. So at that particular size of 5 by 5, I've got 25 pixels for his face. I can do one filtering there. Filter size is 25 by 25. Now I want to filter his whole body. His whole body, let's say, is not 25 by 25. It's something like maybe 500 by 500. Okay. So instead of actually building a 500 by 500 filter, what I do is I downsample the 500 by 500 image so that it becomes 25 by 25. So I downsample it by 5 times. And then I can apply a 25 by 25 size filter. But effectively, that filter is now a larger scale because I'm working on a downsample person. So when I downsample, it's like as if I am compressing the spacing, I'm reducing the spacing between adequate things. So adequate part of the object. So that's the idea of how you can see at a particular image here. If I have this image here, of course, you're not changing the pixel size. The number of pixels is there. But what you're doing is you are reconfiguring the windows over which the pooling is done. So if I have only one big pooling, that means the output of this deep CNN, just one big pooling filter. So I just get one value out of this. That is at its courses because effectively that filter is actually filtering the whole image. Then if I actually have 4 values out of this image, that means I'm only doing pooling on 4 regions of this. So I have 4 values. That effectively means my filter is 1/4 of the size of my image. And then I have 16 of that. and so on. So the idea of SPP net is rather than having a fixed number of regions I pull my image to, I have multi-scale boxes, regions. Okay, so back to this idea. So this idea here, I'm saying that is, the pooling is actually you have a region here, a size here, a particular window here, and then you are actually kind of summarizing a whole bunch of inputs to a small subset of numbers. So the idea between SPP net is across the last layer of the feature map, I don't have window of one particular size. I have window of multiple sizes so that my feature representation is actually capturing features at multiple scales of the feature map. Now is that clear? Did that explanation help you, or is a little bit unclear? Okay, let me try again.
The multi-skill I understand, but I don't know the other people understand or not.
If you're not so clear, just ask me lah. If I can spend a bit more time, because this is one of the things that's coming up often. This is the reason why as you go down the deep neural networks, you are downsampling the image, because actually you're not downsampling. Your filters at the lower, the deeper layers of the image is actually larger scale filters. So downsampling is just an efficient way to do that operation. Here, we're not doing any downsampling. Here, the distinction is a little bit confusing, but here the distinction is you are still taking the features from the last layer of the feature map. You're still taking the features only from one feature map at the end of the deep neural network. So whether you got shallow network, deep network, is the same. You're still looking at the feature map at that layer. But what you're doing is, instead of having one window size, right, you have features from window size A, then window size B, you have 4 features coming out. Window size C, you have 16 features. Then you could have 32 features and all that. And all these features, they are still fixed length feature representation, right? Because all you're varying is you're varying the number, the size of the window line, but still, this region could be of different sizes. What you're saying is that, I split this region into one box, into 4 boxes, into 16 boxes, into 32 boxes. Each box will have different size or different region size, right? But what you're saying is SPP net, the key idea here is I get to vary the scale at which I'm extracting features. I'm not extracting features only at one scale. I vary the scale, but this is coming from only a single feature map. Okay? It's just saying this is a more powerful way of extracting the features. You get more information. So the price you're paying, the feature representation length becomes larger. But it still preserves the requirements of this technique, which is the requirements is that the feature representation layer has to be fixed size. Now it's fixed size, but it's larger. And I'm not just taking, let's say, for example, here, let's say in fast RCNN, the idea is that, okay, at the final level, I'm going to use maybe 16 max pooling boxes. So if I happen to have a region that is 256 by 256, so one of my max pooling box will be 16 by 16 pixels. If I happen to have a region that is 1024 by 1024, then one of my max pooling boxes actually will have 64 by 64. Okay, something like that. This is how the idea would work. And if you happen to have a 1024 by 256 region proposal, then the box is actually, the max pooling box is actually not symmetric. It's going to be maybe 64 by 16. That's the idea. But I have a fixed number of max pooling boxes in this here. For SPP net, you also have a fixed number of max pooling boxes, but you have redundant coverage. Earlier on, I said you have maybe 16 max pooling boxes. Each box will cover one part of the feature map. Here in the SPP net, you have maybe one max pooling box that covers the whole feature map. Then you have 4 that covers the whole feature map. Then you have another 16 that will cover the whole feature map. Then you might have another 64 that will cover the whole feature map. And each of them will give you 1 plus 4 plus 16 plus 64 numbers. So you get 64 plus 16, 80. 80. Then plus 4 plus 1, you get 85 numbers. Your feature vector length is 85 numbers. Okay. All right. Just last call if there's any doubts on this. If there's not, then I'll move on. Okay. I compare and contrast this because later on, you will see something called feature pyramid network. I'll talk about this in more detail later. But feature pyramid network, the idea is that I don't just divide the last stage feature map. I extract features from all the layers of my deep neural network. Okay? So I want to distinguish these from what we call a feature pyramid network versus a spatial pooling pyramid. Okay? There are different kind of pyramid. Just now, the sampling, all that's called the pyramid structure, lah, okay, for image processing. So spatial pyramid pooling, you are doing the pooling on one feature map only, but different resolution. Feature pyramid, you are extracting features from multiple feature maps. Okay, I hope that is clear. You're extracting features from multiple feature maps. It means you're extracting features from different layers, feature maps from different layers with CNN. That's feature pyramid. This is more close to wavelets and filter banks. Spatial pyramid pooling, SPP, you're only extracting it from one feature map, a single feature map only. Okay, right. All right, so I like to show this because this summary from the paper that I cited here is very, very nice. It's beautiful. It just shows you that your input here, you have a convolution network or deep convolution network, and all you get is a large feature map. Okay, and this large feature map, this convolutional part can be big or small. The input can be arbitrary size, just get big or small here. What happens is this ROI pooling, there's an ROI pooling from some arbitrary, can be changed output feature map here. This ROI method will always generate a fixed size feature map here. And this fixed size feature map will be able to then go to some shallow networks for classification and location improvement. So these are class specific, that means they are trained with the class in mind. These feature maps are trained without class. They are class agnostic. Okay, that's why this part here, they don't train so much. They tend to just say, we're not really training this feature extractor, we just use it pre-trained from image map. Okay? So please, sorry, ignore this convolution term here. So we'll go to that. Now, this is where it gets really interesting at this point, because we said past RCNN has converted this part to neural networks. This region proposal is still using selective search, is still using heuristic way of generating proposal. So the open question becomes, can you actually find a region proposal network that is able to be implemented as a deep neural network? And the answer is yes. And what I find most interesting about this work is you are able to use a CNN architecture to specify an object location. And that's nothing else but a region proposal network. It's just basically say that there is possibly a generic object with this particular size in the image. Okay, so pay attention to this, because again, this region proposal network is also not trained in class specific. So faster RCNN, the key innovation is they are able to develop a neural network that can actually propose to you the regions. It's not heuristic now. I can propose the region, and let's recall back. What does it mean to propose the regions? It means you can tell me where the image is that region located, okay, and what is the size of that region. So this is the output of this region proposal network, right? And it's actually doing it in some kind of attention mechanism. And what I like about this area is they say that, well, the region proposals should also really be based on some features, right? Because at the end of the day, you have the region feature extraction, and then you have the region where it's supposed the proposal where it should be these regions and this set of features that are accompanying it. So the way faster RCNN actually built this up is they're saying that, well, I can use the same deep CNN backbone, and out comes the feature map, and out comes the set of region proposals from this same CNN backbone. But again, the feature extraction that comes out and the region proposal is class agnostic. It's not trained on any particular class. Okay, so that's kind of nice, because if we can do this, with all of a sudden make this whole faster RCNN fully neural network based. And the nice thing about fully neural network based is inference time is fixed. You can calculate how many multiplications you need to do. Everything inference time is fixed. And what's kind of nice is we no longer need to actually like redo things for each region in a way. We will see about that. But the region proposer is like, since it's going through the same idea of a CNN, it's going to give you all the regions at one go. All the regions that it could propose is going to propose at one go, at one inference. It's not going to be like the heuristic method where you actually have to find like selective search, you have to find smaller patches of regions and you start merging them, and then you have to come up with 2,000 of these or 6,000 of these, things like that. It's not like that. It's one-time inference, and then you get all the region proposals that you need. Okay? So this is the secret how faster ICNN is able to become faster. He converts everything into deep neural network, and he makes sure that the very compute intensive part, that is proposing where the regions are and getting the features of each region, this they effectively reuse by only performing one round of inference on the deep CNN. Let's see how they do this, and this is very interesting. So the region proposer network is also a neural network. Okay, it's also a neural network, and it's coming out of a convolutional layer. So again, there's a common convolutional backbone that is going to the feature extraction, and output of this convolutional layer will be a region proposer network, which is basically taking the output of the last feature map of the convolutional layer. It's going to take that, and it's going to generate a map of proposals. Okay, and that map of proposals will actually have a fixed number of proposals that will come out of it. Okay, so again, it's a neural network that is going to look at the last stage feature map of the entire convolutional layer, and it's going to propose a fixed number of regions. And again, what do we mean by regions? We need its location, its XY position, and the width and height of the box. Okay, so as you can see, the reason why we make that statement is because it becomes a regression problem, right? Because if the way you're specifying a location is the center of the box, the width and the height, you are actually predicting a regression problem. You're actually using all the input features just to predict these four values. What is these four values? The XY position of the bounding box center and the width and the height of the box. Okay? So that's what is really interesting about this. That all of a sudden now, this region proposer network is able to generate proposals of the region, and then for a fixed number of regions, is able to give the width, the height, and the center. And then based on the number of regions, you will apply it to the ROI pooling. So now, the first two steps, region proposal and feature extraction, you do in one deep neural network inference step. You get all of that. But you still need to repeat the ROI pooling for every single region, right? Because for each region, you get the bounding box size, then you will do the pooling of the features on the last stage of the feature map. So that's the attention network part. It's because the outputs from the region proposal network will be applied like an attention. It's will be applied in a way that you only consider certain features in the feature map for that particular region proposal. And what I find interesting about this is, again, this idea, how do they train these two this region proposal network, right? Because the region proposal network is not class specific, it's class agnostic. How do you train it? So they do a kind of 4-step training. First, they train the region proposal network first. Okay, they get some initialization of region proposals. Then they train the full fast ICNN. So when I talk about fast ICNN, I'm just talking about these parts here, the fully connected layers and the ROI pooling. Okay, then they train this part here to get the classification and the fine-tuning of the bounding box, right? Once they got that, they retrain again the region proposal network so that you can refine, make this accurate. And after that, with more accurate region proposals, they will train the fast ICNN portion again. And again, here it's interesting, they're still using the same multi-task loss. So the loss will actually come from, region proposal network will come from how accurate are we doing the classification from the classifier part. and how accurate are we predicting the bounding box. So the region proposal network, even though it's class agnostic, it is being trained on class specific data. That means there is a fourth region proposal network here, proposal generation. You are training this on this data, class specific data. Right? Okay, so this is a further refinement of how they can actually achieve region proposals using CNN. And this is interesting because, again, if you think about it, I'm using a CNN to give you results on bounding box with different sizes and at different locations. So what they do is that they actually specify that each location at each position in the at each pixel of the feature map, you are going to predict A regions. So if you have a 256 by 256 final layer of your feature map from the convolutional output, you're going to have 256 by 256 times K predictions. Okay, and these K region predictions, they call it anchor boxes. The anchor box is going to be centered on that particular voxel, but it's going to have different size. Okay, and what they do, they try to have some diversity here. They have different sizes of the anchor box, different aspect ratios. So they said just have 9 of them. So there's 3 scales and 3 sizes. Okay, so what they're predicting is actually you're predicting a feature representation, and then you're predicting you're predicting the size of and the location of the bounding box, and you're predicting the score, whether this is a region or not a region. Sorry. This was mistake. It's not predicted based on the the class of object. It's actually region or no region. It's a different set of laws. So the region proposal network, there are 2 outputs out of it. One is the 4 coordinates for each position. That is the center of the box and its width and its height. So there's 4 values. And then there is a score. The score is saying that is this a region or it's not a region? Is it a valid region or not a region? It's supposed to be object agnostic. So you have this number of coordinates. This number of outputs coming from the convolutional layer. So this convolutional layer will be slided across the entire feature map. So at every position, you'll be predicting 9 boxes out of that location. Okay. Now this is a little bit confusing because on one hand you think that 9 boxes is the boxes necessarily centered around that pixel. No, because you can actually predict the XY location to be something really far off. It's like saying I have this little 3 by 3 window. I'm looking at the feature map, and from this 3 by 3 window, I can tell you where in the whole image I'm predicting that there is an object. Okay, that there is a possible object without knowing what that object is in advance. I find this to be quite miraculous, but it actually works. So it's very interesting to study this. So if you think about this, one of my initial difficulties when understanding this was trying to understand how is it possible you don't see the whole features in the entire bounding box and you can still predict. And this is saying exactly that. I think what faster RCNN and the bounding box is actually predicting is, if you look at the actual bounding box, okay, this is actually a bounding box that you want to predict. But if you're doing a 3 by 3 window, it's sort of saying that I'm actually having if I'm doing convolutional 3 by 3 on this, I'm actually looking at the feature map at this location, and this location is going to give me 9 predictions. One of the prediction could be the center is here, this is the size. Then I'm going to be looking at this patch of features, and this patch of features can also tell me this is the center location and this is the size. So it's like saying that this K region proposal is like you are actually looking at small patches within the image itself and saying that, okay, there could be one object at this point, at this point, at this point. So it's a very interesting underdetermined problem. To me, it's fantastic that you can actually predict a region just by looking at a small patch on the feature map. But that's what faster RCNN is doing with the convolutional region proposal network. And I think this is a fantastic case study because what they're suggesting, and they're taking advantage of, again, this pool to state, they're saying that region proposal, I don't need to be so accurate. I need to be somewhere there. and then I can rely on the class-specific regression to really update my bounding box. So if I need to have some kind of course region, which you can actually think about it like finding out where should I pay my attention to, and here the attention is less interesting in the sense that it's just more like a box. This is one way to actually generate that. So I find it interesting. Okay, and why do I find it interesting? Because it looks like it is a third method to predict, to do multi-scale prediction, multi-scale object feature representation, and multi-scale feature prediction. What do I mean by that? The first type of multi-scale, as you can see, is as what you've been doing. The first step is you actually get features at one scale. So the feature map is this big because the filters are very small. Then you downsample the image, you retain the filter size, so you have less pixels, but effectively what actually means is not that your pixels become smaller, but your pixels actually represent a larger region, a larger filter on the object. Because you discretize it, because you discretize on a fixed field of view, if you have a larger window, of course, you have fewer numbers to represent from a fixed field of view. So multi-scale can be you actually have you actually resize the images multiple times, and then you just get the features out of it. Or a second way would be you actually change the size of the filters. You make them bigger. That means you're not doing any downsampling. You're just making the filters bigger. The third area is actually the bounding box point. It's basically I'm looking at just a fixed number of pixels, but based on the fixed number of pixels, I can predict features, or I can make some kind of prediction on different scales and different locations of this object, which is this kind of blue boxes. So this is why I thought it was kind of interesting to highlight this, because the anchor box appears to be a kind of crappy, but it seems to work. Third way of actually getting multi-scale predictions. Why? Because the prediction is you're still making a prediction on where on something within that window, right? So that something in this case is whether this is a valid object or not in this region. And it's multi-scale because you're predicting the kind of bounding box or region size of this object. Whereas in these two approaches, the region size is actually fixed by the filter size. So here you're looking at the fixed size or fixed number of pixels, and then you're kind of predicting the window size. You're saying that I can say something about this large window size looking at only these few pixels. So it's kind of interesting. But I want to highlight it because I want to actually share that we are still at this point, other from the feature pyramid network, which I briefly mentioned, we're still at this point only making our decisions at the final layer of the convolutional neural network. You're supposed to be doing multi-scale prediction, but how are you doing multi-scale prediction only on the final layer of the feature map, ignoring the features of all the other scales? And that was a problem with this. Okay? So this is where it becomes interesting. Okay? Right. So far, what we talked about is you have this baseline convolutional neural network, and this is really pre-trained, and it can be as deep as you want now. It doesn't have to be AlexNet, it can be ResNet, DarkNet, and all that. And this is just getting feature representation for the whole image. Okay, and then there's this fancy part that is class specific, where we somehow have a mechanism. We are able to do pooling to get a fixed size feature representation for whatever region. So every region we want, we just get a fixed size representation. So you have to repeat this part multiple times for every single region you want. And then you can actually have a prediction network that actually tells you the class and refine the location and size of the bounding box. And just now, what we talk about is from this feature representation, we can also predict the regions, the proposed regions. Okay. And these proposed regions will be, again, you propose its location and you see whether there is basically an object there or not. And those regions where there's object, you will apply to actually get this ROI. But the problem here is, again, at this point here. At this point here, if this path here, I can generate with just one forward inference step because it's fully convolutional, right? No problem, it's fully convolutional. I can generate just one inference step. I get all my region proposals with just one run of the deep neural network. But this part here, because I am converging to a fixed size feature representation, I need to run this part as many times as there are region proposals coming out of this network. So the open question is now, can I convert this portion here, which is this mapping of uh, pooling, max pooling, into some kind of fully convolutional network structure so that I can just run this whole thing as one forward pass fully convolutional network. Okay? And this would be the way how I really save on iterations, right? Because again, we started out with RCNN. RCNN was very compute intensive because you have to iterate so many times, and we've been slowly trying to reduce the number of iterations by reusing features. And we do this by saying that fully convolutional network, I just need to do the inference once. I get all the features I ever need for everything. And now we are kind of stuck at this last point. Can I just get features for all these regions without having to kind of do this fixed ROI region of interest mapping? And the answer is yes, is the RSCN structure. And I find this also very cool and very interesting. Why? Because they have somehow find a way to do. Okay, previously we were just saying that I can pick some arbitrary region here. Okay? The size and the location of this region is the output of this network. I can pick some arbitrary location here. I have to divide it up into a bunch of max pooling boxes, and then I get a fixed size feature map. How to convert it into a convolutional architecture? The interesting point is that this fixed size feature map, each value of this feature map represents a region, the object, a spatial position. So each size of this feature representation will represent a region of the image. But instead of confining the region to the filter width, they have transformed that region into a spatial channel. This is brilliant. Okay? You have somehow find a way to move from a fixed spatially confined structure. You make it into a channel. That means it's one additional channel, filter bank. You can get the region-specific information in this output for free. So this I think is pure brilliance, because I just find it so cool. You actually can change a spatially confined network into a channel kind of information, and then you actually can make it fully convolutional. So this sort of, to me, it actually allows you to now, you can get fixed size feature representation, even for spatially limited or spatially restricted things. This is just idea that your filter, the filter in a particular channel can actually encode space-specific information, and then you can actually apply a fully convolutional network for that. So with RFCN, we finally are able to achieve fully convolutional object detection. And this methodology, you actually have two distinct outputs of the network. One is the region proposal. Second is actually the classification and the localization, the refinement of the location of the object. So you would probably still have to generate these, but again, because you don't have to do the max pooling multiple times, you're just kind of segmenting out, in a way, you're segmenting out which region that I'm looking for this. You can really reduce the number of computations at this point. Yeah? So this is, I think, a very interesting application of this. And I actually think that this method can be applied for many other kind of techniques. Because again, if you look at this idea is that rather than confining myself to kind of a spatial extent of the window, I can actually define convolutional channels that are saying something about a different spatial location within my image. So I think that's kind of really powerful. Okay, so apart from that, the feature pyramid network, as I mentioned, is also an attempt to try to improve the feature representation you have going into this network. Because now you can see object detection, we have fully convolutional structure all the way here and here. This could be very fast, and the reason it could be very fast is because you throw away most of the iterative steps by reusing a lot of the feature representation using fully convolutional networks. And the key question is the accuracy at region proposal here and the accuracy at object detection will depend on the quality of the features here. And so people are like, yeah, it doesn't make sense if I've got a very deep network here to just use the features here. I'm going to start looking at the possibility to use features from multiple layers of my neural network. Okay, so this is just different architectures of showing how this could be done. Okay. I'm just showing you that it doesn't have to be this only. The one way to do it will be here. You have a feature representative, feature map going like that. You just take outputs at each layer here. Okay, and this one here, the idea is that you are actually literally scaling down the images going through different networks. This one is you are not scaling down the images, you are actually performing a second filtering on the first layer feature map to get the outputs here. This is what we've been talking about the RTN and faster RCN previously, that the feature networks like the SPP net and all that were only taken from the final layer. And where we're going with this is we are actually wanting to take it from multiple layers here. And this is very interesting too, because you look at this, you're like, yeah, they could also take it from here. But why are they doing this? And I actually think the only reason they're doing this is because they want to leverage on the success of the UNet architecture. Because again, these convolutional networks is a kind of a compressing encoder structure is going down deep into that. But again, with UNets and that kind of encoder decoder structure, you actually have the ability to get more cooler kind of more cool kind of feature representation. And the second reason for this is also because if you're just looking at taking from here, you cannot deal with skip connections. So if you look at this looks like a encoded decoder structure. It looks like a UNet, but it also has the form of a ResNet and a DenseNet, where you actually have skip connections going to the next layer or residual connections going to the next layer for that. So this feature network is defined this way to take advantage of these two kind of advances in the architecture, which have been proven to actually allow you to go deep. So the reason we are using ResNet and DenseNet and again UNet is because again with this feed forward and skip or dense or residual connections, we really can train deep networks, really deep networks. And when you can train deep networks, of course, your feature representation is more powerful. So this is the reason why we're going for this. This is the key idea of feature pyramid network. And this is just showing you how it possibly could be done. It could be from this previous layer, they do upscaling, okay, and that would be that fractional convolutional or a forward convolutional from segmentation. And then this layer coming from this layer could also be another convolutional block in general. It could be a skip connection, meaning that one by one convolutional, you just the values are one or you do some kind of weight. Okay. So I would say that feature pyramid network, finally, why they're including it is because they're saying that everything now is very fast here. To get more accuracy here, we just need to strengthen the feature representation here. So why not look at the full network rather than just the outputs here. And again, here, this is an excuse to use these two, in my opinion. You can apply feature pyramid networks to RPN, which is region proposal networks. Sorry, RPN stands for region proposal network as the fast RCNN. And because this is already by default multi-scale representation, it sort of doesn't make sense for you to use multi-scale anchor boxes. Okay, it doesn't make sense for you to use multi-scale anchor boxes anymore because you can actually predict at the proper scale using the features for that particular scale. So when you're using the feature pyramid network type of features, if you're still doing anchor boxes, but your anchor boxes most likely will have different aspect ratio, not different scales anymore, because you will actually have maybe 3 anchor boxes predicting from here, another 3 anchor boxes from here, another 3 anchor boxes from here, something along that line. Okay. All right. So this is kind of the summary of what I think this has evolved into. So you got the kind of feature maps from all these layers going into the region proposal network, and is also this feature representation can also be used for the classification for that. Okay. At this point, any questions so far? Anything that is not clear that I can further clarify? I guess I've not lost you guys, have I?
No, from my side.
Okay, so I've not lost you guys and things are okay. So let's go on. Okay, this would effectively cover. Okay, no, there's one more part of it. Uh, so if you're looking at this object detection kind of architecture that we're building up to, the way I presented it to you is I don't present it as a distinct set of techniques, but I try to let you share my perspective that it's really a sequence of gradual optimizations from one technique to the next. And if you were going to actually implement state-of-the-art object detection, you understand these key ideas, you can just combine them all together. I don't see why that should not be possible. And one interesting thing about this approach, where if you can start designing region proposals from a convolutional network and all that, why not predict the segments in one go as well? Right? Because it's kind of the same architecture, is fully convolutional and all that. So this is what the mass RCNN does. Like, all it does is it says that in parallel to your region proposal network and your object detection and classification network, I add another third network which is still taking data, the feature representation from my base CNN, and this is called the mask. And the mask is nothing else but a segmentation mask. So I can actually do that, and I can do that because I'm taking advantage of this multitask loss to train, not just the class, not just the box, but the accuracy of the mask. And the only maybe innovation here I would say is there is some kind of fine scale alignment of the pixel identity, because you're taking the features from a cost, the last set of feature map, but your segmentation mask has to be mapped to your initial input, the resolution of your initial input image. So that's why you have to do this ROI alignment, which I won't go into it because it's a detail. But it's just this idea that, okay, since you already found a way to create to generate proposals of regions, you already found a way to classify and to define the estimate of the bounding box, you might as well do something to in parallel with that to predict the segment to further the localization. And it's kind of an interesting idea, because it's this idea that once you got some kind of base representation, you've got multitask classifiers. So it's kind of interesting because, again, if you look at it in a way, these are actually multitask classifiers. This is like object detection is actually a multitask classification regression problem. And what you are actually doing in a certain way is you are there's a bit of transfer learning going on here, right? Because the benefit of this would actually help this and all that. So there's a bit of meta learning going on here as well, because we're trying to ensure that that the multitask loss is helping you to learn the best features for all of these combined, right? So I'd like you to recognize object detection is an instance of a multitask neural network. It's doing multiple classification, and it's an instance of meta learning and transfer learning all rolled into one. It's kind of interesting to think about it from this perspective. Okay. Right. It's 4:30 already. Can you guys stay for another half an hour, or you're busy?
I have an interview at what 4:30.
Oh, you have interview at 4:30. Okay.
But the rest of us can continue if there's no time limitation for them.
Okay. Right. So I guess I'll just go on to YOLO, the second part, and then I'm recording this, so maybe you can access this if you're interested.
Okay.
All right. All right. So the next set of methods would be those methods that don't explicitly generate the region proposal. It's still somehow used inside this, but it's just there's no place in this network that you can actually pull out where is the proposal of the region. That's the only key difference. But the way it's presented, the way this is described, to me, it sounds like they're still relying on region proposals. It's just that you cannot actually pull out the proposed regions anywhere in this network. So it started with YOLO version 1. And the idea for them is they're just saying, like, okay, I'm going to divide my image into a grid of 7 by 7 patches. Okay? So no matter what my size of my image is, I'm just going to divide it into 7 by 7 patches. Okay? And in each of this patch, I will tell you, in each of this patch, I will propose two bounding boxes and tell what object is belonging to this patch. Okay, let me repeat that. So this idea of YOLO version 1 is, I'm not going to just do everything like propose regions everywhere and all that. I'll take a different approach. I start carving up my image into patches. Okay? Each patch, I can tell this patch has what object or no object. Okay, it started like that. That means it's kind of doing a limitation. I say that I don't want to detect all the possible objects in the image, but I just try to be reasonable. I want to go fast. I just say in one patch, I allow myself to predict one object. And given that one object, I allow myself to predict two bounding boxes. Okay. So that's the idea behind this. There's an S by S, your image, whatever size that it is, 2 by 6 by 2 by 6, 1024 by 24, you divide it into 7 by 7 patches. And each of these 7 by 7 patches, there's going to be two values of bounding boxes, X, Y, width, and height. And in this case, there's 20 class probabilities from the example they give. That means there are 20, probably 20 objects you can get. And again, this is the output here. This 7 by 7 is the 7 patches, and 30 is the bounding boxes plus the 5 class probabilities. So there's 7 by 7 by 30 numbers that your network is predicting. Okay, just to be iterative, the way they frame the problem is they just say, I'm going to make a fixed number of predictions. I'm going to divide the image into 7 by 7 patches. Each patch, I'm going to predict whether the object, one prediction, what is the best possible object that is there, and I'm going to predict two bounding boxes. Okay, and the way they do this is fully convolutional all the way, and that's fully connected. That's it. It's simple and elegant. Perfect. And it's just this basic idea again. You can predict the bounding boxes by X, Y, W, H. Okay. Right. Again, how do they do it? This repeated idea, there's a multitask loss. Okay, there's a task for localizing the bounding box. There's a task of your confidence in whether it's object or not object. There's a classification loss. So you look at it in a way, your network is being forced to learn by a bunch of constraints. But rather than separating it out into a separate network, right? Because in separate network, you're still teaching it a constraint. What's the constraint? Region or not region? Object or not object? Here also you have that one, the confidence, whether it's an object or not. But the difference here is you train it into one mega large loss function, and you do not explicitly get the proposal for regions. Rather, you're just saying, instead of thinking about it in terms of, I propose regions, then I tell you whether the region is object or not, I say this patch of the image, what is the most likely object that is there, and what is most likely localization. Okay? And because of that, YOLO has this thing that it has to do, that because it's predicting an object, right? And then it's predicting the bounding box of the object, right? And you have different patches, 7 by 7 patches. It's possible for you to actually predict different bounding boxes for the same object. Okay? So this is what non-maximal suppression is for. It's actually looking at, okay, if there are bounding boxes that are very, very similar, like sort of predicting very, very similar object, I try to suppress all of them except the best one. So it's this idea that rather than having 3 bounding boxes for this axis, I try to pick the best one. I throw away the rest. So there's this important step of non-maximal suppression. And I like to highlight to you this non-maximal suppression is also important. I wouldn't say you don't need to apply it for faster RCNN. Maybe faster RCNN, because of the way the region is done, earlier in the selective search, you might not need it, but maybe from this this particular vision proposal network, you might need it. Is this idea if you don't handle it correctly, if this non-maximal suppression is not handled correctly, you will reduce your ability to detect multiple instances of the same object that are close together. I repeat, if you don't handle this non-maximal suppression of the bounding box properly, you will reduce your ability to detect multiple instances of the same object close together. I give you an example. if you look at this taxi image again, okay, how do you know these 4 or 5 bounding boxes? Is it referring to the same taxi, or are you trying to detect 2 different taxis? This is why I said the multi-instance object detection is the most challenging. So YOLO version 1, this is the key idea. YOLO version 2 is all about trying to steal ideas from faster RCNN to kind of improve things. So instead of actually predicting 2 bounding boxes per, per, per region, per patch, they actually predict anchor boxes centered at that particular cell. Okay, so they move away from bounding boxes to anchor boxes. And what they sort of actually say is that if you want to predict the position, center point coordinate x and y, and the width and height, this is actually not so accurate compared to you actually limit the number, you predict an offset from the anchor box. That means what it's saying is that instead of actually predicting the arbitrary XY position and then hit the front of the box, which is not so accurate, they're saying that a priori, you say at each kind of pixel, you have a bunch of anchor boxes. These are predetermined sizes and all that. What you're doing is you're predicting the change, the offset of this anchor box. What is the offset of the true bounding box from the anchor box? And what is the offset in terms of its size? That means you can actually make this as a value, you can get it as a value of 0 to 1. So it's a relative size to predefined anchor boxes rather than absolute size. And they find that this improves the accuracy. And again, they are using some of the same tricks again, like using the pyramid network, multi-scale anchor boxes, and fully convolutional architecture. So YOLO version 2 is actually sort of like this core idea, but I just do a bit more here, borrowing all the ideas that we discussed previously, like to define the feature representation. That's why they talk about feature pyramid network. And then instead of just limiting 2 bounding boxes, they go the anchor box way. And I think the interesting thing about YOLO version 2 is they introduced a new backbone network called the darknet 19. So the darknet 19 is slightly different from ResNet. It has more similarities to Inception because the idea is basically to get sparse network connections. Is this idea from a paper called network that you actually have very, very sparse connections that go deep. So the darknet is actually a little bit closer to the Inception style of creating weights, right? So darknet 19 was introduced in YOLO version 2, which is a different backbone. And again, in YOLO version 3, it seemed to be just even more tweaks to make it faster. But the most important, I think, was to introduce a deeper version of darknet, darknet 53. And what's actually interesting is you see that the baseboard darknet 53 actually has order of magnitude kind of accuracy, same as a deeper ResNet 52, ResNet 101. So it's something for you to actually consider that maybe in certain cases, the feature representation from darknet, which is actually following a different paradigm for neural networks, talking about very sparse, deep connections rather than convolutional and residual connections. Okay, I'm going to be finishing up on YOLO at this point, and the only additions to YOLO, the further improvements, SSDNet, RetinaNet. SSDNet, which is this one. Okay, this is YOLO. YOLO is all these convolutional layers. Fully connected layer gives you the output. Okay, just reminding all these convolutional layers, fully connected layer gives you the output. That's YOLO. Okay, SSD has only changed. Instead of fully connected output, the output is not only fully connected, it is convolutional all the way. And then you are taking the feature maps from each layer into a final classifier. That's all that SSDNet is doing. And it's fully convolutional all the way to get category, to get the offset, and to get the boxes size. That's the only difference. It's just an architectural difference to get it fully convolutional instead of fully connected. That's SSDNet. And RetinaNet, the only difference I can see is SSDNet with a feature pyramid network. You're just pulling all of this out. So sorry, it's not that different. It's just more of adding all the best practices and they just call it a new network. But RetinaNet, the interesting part, I think the most interesting part, I think, is their idea of how to handle the class imbalance. And we're back to this fundamental idea that in object detection, you have many more instances of background. That means there's no specific class versus class examples. And there's some estimates that the class imbalance of this is a ratio of 1,000 to 1 or greater. That means by virtue, you actually have many, many more examples of background rather than object of the class you want. And this is a problem because all of you probably are very familiar right now. If you have class imbalance, your network will probably default to become very accurate on the class with the highest imbalance. And then all these other classes will just perform shitty. So if you have semantic segmentation and all that, right, you've got this background segmentation is great. Your network is going to be great at predicting the background. It's not going to identify the objects at all. So this is a problem. How do you actually try to train this and kind of still solve this problem? There are ways to do it. There are some of these very fancy techniques where they select image samples so that you actually see more of the class samples. But here is an interesting way. It's called a focal loss. And what it's trying to do is just trying to decay the probability of the highly, it's trying to decay the contribution of the highly probable classes. So this is cross entropy loss, is minus log the probability of that particular class. Okay, and the probability of that particular class is just how many times it appears versus a certain number of predictions and all that. So what the focal loss basically is, it is reducing the cross entropy law by some kind of rule. That's all it is. What is this rule? This rule is dependent on the probability of that class. So the higher, the more frequent you see this class, the more it will discount the loss of this, right? So that this loss of this very frequent class does not dominate your loss function. Okay, so the rule is just really 1 minus that probability to some power gamma. Okay, the gamma can range from 0.5 to 1 to 2.5. This is a hyperparameter gamma. So 0.5 to 5 is okay. But the key idea here is just for the background class, it is performing an attenuation of the loss function so that the background class does not overwhelm the other classes. So this is kind of interesting because in a situation where you actually have class imbalance, you may actually choose to use the loss to help you manage a little bit the class imbalance problem. And maybe the way the focal loss will be applied, I guess you probably have to step through your strategies where you might want to train preliminary with balanced set first, and then gradually increase more of the imbalanced set and then focal loss. There are many ways to try to explore this, but the idea of a focal loss is very interesting because it's actually reducing the contribution of the imbalanced class, which in this case happens to be the class you're not so interested in. Because if you think about the standard classification problem, if I have more examples of a particular class, that class is going to show up more often. So I probably want to be more accurate on that prediction, and that would be right. But in this case, it is not so much that this class show up often, but rather is we just have more background than classes, than object classes. Okay, so this is just another visualization of how SSDNet is improving on the YOLO. You have additional convolutional layers that are just taken out, the feature representation taken out for decision making. And in RetinaNet, instead of additional convolutional layers, you're pulling it out from by a feature pyramid network and adding that up together. So this is sort of like thinking about it as stick connections, UNet, that kind of thing. Okay, so in summary, we talked about object detection, deep neural net using deep neural networks. There are two kind of standard approaches based on deep neural network. One, explicitly you design networks to propose the regions, and then based on the proposed regions, you classify what is the object in that class, and then you refine the position of the bounding box. Number two, you just have a direct prediction on the object and the bounding box. You're still taking into account the region proposalness, but that's like indirectly through the loss function, the multipass loss. Okay, I'm done with this material. Any questions from the point of that you would like to clarify?
I don't have any.
Okay, thank you, Ibrahim. Yeah, just going to wait for a minute or two more. If nothing, then we can end the session. Then maybe I'll work with Adele to get the next date and the next set of topics that we can cover. Yeah, I think I will also share with Adele this recording, just internally for those who are interested.